Every single time you hop on Wi-Fi or fire off an email, you're actually using an invisible map. So today, we're going to unfold that map and explore the hidden shapes that connect our entire digital world.
I mean, it really does seem like magic, doesn't it? How does your data get from point A to point B? Well, it turns out it's not magic at all. There's a specific map, a hidden architecture that makes it all possible.
Okay, here's a great way to think about this. Imagine you're setting up a massive video game party. You've got all these computers, right? You have to figure out the best way to physically connect them all. Or think bigger. Imagine you're designing a city. Are you going to build one giant main road, a central roundabout, or a separate road from every house to every other house? Each of those designs is a different kind of map.
And that map, it actually has a technical name, network topology. It's just a fancy term for the physical or logical shape of a network. Every device on it, your laptop, your phone, that printer in the corner, is called a node. So topology is just the blueprint for how all of those nodes are connected to each other.
But why should you care what the shape is? I mean, it's not just for looks. The layout you choose has massive, real-world consequences for how well your network is actually going to perform.
Yeah, it all comes down to a few really key things. The shape you pick directly impacts how much it's going to cost, how fast it'll be, how reliable it is, and how easy it's going to be to add more stuff to it later on. It's this constant balancing act between these four factors.
All right, so let's take a tour of the most common network shapes. Think of it as a guided trip through the different ways we build these digital cities.
So for our first stop, I want you to imagine a long, single-school hallway. That's it. Every single classroom has a door that opens up onto this one hallway. Got that picture? That's our first topology.
This is called a bus topology. All the nodes, or devices, are connected to one single main cable, which we call the backbone. Now, when one computer wants to send some data, it basically just shouts it down the hallway. Every other computer hears it, but only the one it's actually addressed to pays any attention.
So, what's the deal with the bus? Well, here's the big trade-off. It's super cheap and incredibly simple to set up. Perfect for those old-school LAN parties. But its weakness is gigantic. If that one main cable breaks anywhere, the whole network goes down. Game over.
Okay, let's move on. For our next stop, picture a busy airport. You know how all the gates connect back to one central terminal building? Keep that image in your head.
This is a star topology, and honestly, this is probably the one you're most familiar with, even if you don't know the name. Every single one of your devices connects directly to a central hub. Think of your home Wi-Fi router. All data has to pass through that central point to get anywhere else. And here you can really see its core strength and its major weakness. If the connection to your laptop fails, no big deal. Your phone and your smart TV are still online. But it has a single point of failure. If that central router dies, everything goes down with it.
Our next destination is a little bit different. Imagine you're all sitting in a circle, and you need to pass a note. You can't just throw it across the room. You have to pass it to the person right next to you, who then passes it to the next, and so on, until it gets where it's going.
This is the ring topology. All the nodes are connected in a continuous loop. Now, to keep things orderly and stop data from colliding, these networks often use a digital token. You can think of it like a talking stick. A computer can only send data if it's currently holding the token.
So the big advantage here is that the token system makes it really efficient when there's a lot of traffic. Nobody is shouting over anyone else. The downside? Well, just like the bus, it's incredibly fragile. One single break in that ring, and the entire circle of communication is completely broken.
Okay, for our final stop, we're going to think way bigger. I mean, think about the entire internet. It's not just one road, right? It's a massive overlapping grid of highways, back roads, and scenic routes all connected together.
This is the mesh topology, and it is the absolute king of reliability. In what's called a full mesh, every single node is connected to every other node. So if one connection goes down, who cares? The data just instantly finds one of the many other available paths. It's essentially self-healing. And this idea actually goes way back to the internet's predecessor, ARPANET, which was specifically designed to survive a massive attack by always having an alternate route.
So what's the catch? Well, mesh gives you the ultimate, the absolute peak of reliability, but that comes at a staggering cost. The sheer amount of cabling and the complexity of managing it all can be a total nightmare. For most situations, it's just way overkill.
Okay, let's just pause for a quick recap.
Looking at this, you can really see how each topology, with its analogy, has a very clear main benefit and a really major drawback. It ranges from the cheap but fragile bus all the way to the super reliable but insanely expensive mesh.
So we've seen these pure forms, but how does this all actually work in the real world? Because, it's not always so neat and simple.
The truth is, most large networks aren't just one type. They're hybrids that mix and match to get the strengths of different shapes. A fantastic example is something called the tree topology. Think of a university campus. Each building might have its own efficient star network inside. Then, all those individual stars are connected to each other using a simple main bus cable that runs across the campus. See? You get the best of both worlds, manageable stars linked by an inexpensive bus.
Okay, let's bring all of this right back home. How do these abstract shapes apply to the network that you're using this very second?
And this, right here, is where it all comes together. The network inside your house, connecting your phone, your laptop, and your TV to your Wi-Fi router, that is a classic star topology. But the global internet that your router connects to, that is a massive, self-healing mesh, built on that core idea of redundancy to give us the maximum possible uptime.
So, we'll end with this question. We've seen how these shapes define our digital connections today, but as our needs for more speed and even more reliability just keep growing, what's the shape of the network of the future going to be? That's something to think about.